Welcome to Invisible Machines, a podcast where we explore the expanding world of AI agents and conversational technologies. I'm Josh Tyson, co-author of Age of Invisible Machines, a best-selling book all about the agentic approach to automation and the pursuit of organizational AGI. I'm joined each week by Robb Wilson, CEO and co-founder of OneReach.ai. Robb and I wrote Age of Invisible Machines over countless hours of conversation, much like the ones we have each week on this podcast. Robb has spent decades researching and deploying conversational technologies, and Invisible Machines is where we share big ideas with fellow AI insiders. We're continuing these conversations in partnership with UX Magazine because attention to experience design is paramount to the proper deployment of AI agents, or invisible machines, if you will. Today, we're bringing you an in-action episode exploring the world of computer vision with Jason Corso, professor of robotics at University of Michigan. Jason is also the co-founder and chief science officer of Voxel 51, a leading open source software framework for the development of computer vision datasets and models. Though often associated with things like self-driving cars, as you'll hear us discuss, computer vision is deeply connected to the burgeoning world of AI agents. We don't hear as much about computer vision as we do about, say, LLMs, but giving machines the ability to see things opens up a vast trove of contextual information that can push AI agents into new and exciting territory. As with all of our in-action episodes, this is a visual demonstration. Jason shares his screen as he walks us through some computer vision models and datasets, and we recommend watching it on the Invisible Machines YouTube channel. As I've already hinted, computer vision is going to become an increasingly critical component to multi-agent systems, so let your brain feast on this in-action episode with Jason Corso. Invisible Machines is produced for UX Magazine in partnership with OneReach.ai. Named a leader by every major analyst group, OneReach.ai's Generative Studio X platform was built specifically to facilitate the no-code orchestration of AI agents. GSX is trusted by global giants like PepsiCo, PwC, Deloitte, and DHL, but anyone can experience the level of agent orchestration we talk about on this podcast through interactive demos at OneReach.ai. Now, on with the show. All right, well, Jason, delighted to have you on the show. Thank you for joining us today.
Great to be here, Josh.
Robb, a pleasure as always seeing you. So, Jason, one of the things that we were sort of interested in talking about before we get into the demo portion of this episode is, with LLMs kind of bursting on the scene, I feel like natural language understanding is now kind of a well-explored topic. There's a lot of people discussing language comprehension, and it's sort of top of mind for a lot of businesses and organizations. But you work in AI vision, and vision understanding is something that maybe doesn't get as much attention as it should, because it feels like it will be a very big piece of sort of the AI systems that come to kind of, be present in every aspect of our lives in the near future. Would you want to talk a little bit about video understanding and like some of the key challenges there that you've been working around?
Absolutely. Yeah. I mean, I totally agree, right? We're humans, we communicate, we connect with people through language. So it's natural that NLP, or natural language processing, or NLU, natural language understanding, through the excitement of the recent LLM boom, kind of came first. But, as humans also, we, at least those of us who have the privilege of sight, we use our vision quite a lot, right? Like there's a vast portion of our brain that's dedicated to vision. When I teach computer vision, which is kind of the name of the discipline in AI, is formally called computer vision. At Voxel, we call it visual AI, just to connect it to like the action you take. But ultimately, computer vision is the problem of like turning visual data into insights that then you might want to go act on. But when I teach computer vision, I normally, like day one, will normally say something like, how many of you walked into a wall on the way to the classroom. And like, well, no one said, obviously no one walks into what, like, right? Why? Because you're so good at seeing. We don't think about how good we are at seeing and yet how complex the visual world is, right? Like I'm looking at you through this, video recording right now. Half of my other view is a beautiful fall foliage. The other half is a whiteboard, right? Like tons of complex scenery right in front of me here, but I can focus on you and I don't have to think about that. But if I wanted to think about what was on the whiteboard with the student or whatever, right? Like that would also be possible. And I think, the field of computer vision, which is, it's actually older than you think. I believe it was first a problem in computer vision was first investigated at MIT, I believe in like the mid 50s. And although we've seen massive growth in the last 5, 10 years, it's definitely a well-established field. What we like to say at Voxel 51 is that, this is 2024 is the year of visual AI because, like where language got the last few years, right? Like now
Yeah,
everyone's realizing like if we connect visual data to language data to make other inferences, whether or not it's like I don't know, like a thinking cap that you can put on to help you cook a meal that you've never cooked before, and it can kind of point to you what to do, or it's like an objective. Well, I like the NFL, if it's like an objective ref for the NFL, wouldn't that be nice? That we don't have to think about flags being thrown all the time or whatever, right? So, there's just a huge amount of opportunity in the field of computer vision. Um, and it's not we're not alone, in this conversation, right? There's something like I can get you the stat if you want, but like 85% of all the bits that go through network routers on the internet are actual video bits. Like think about like your iPhone or your Android phone, like whereas 5 years ago it used to take actual photos. Nowadays, like when it takes a picture, it's actually taking a short video and then you get to scroll through it forward and backwards to
right.
pick the right frame, right? So just a huge amount of opportunity with the visual world. And, I think, it's high time to that, it's exciting that we're seeing so many startups coming online and so much
Yeah.
growth in the domain.
Yeah, and there's 2 areas that like, one thing is language, and it's not that vision is void of the language problem, like, it's a lot of it is, like, converting image to language, so it kind of encapsulates both paradigms, and then also the complexity, you know, language has this, like, typical built-in benefit oftentimes of being somewhat focused. I sort of think of it as, like, trying to do, voice detection in a room with 100 people speaking at the same time, right? Because that's kind of what visual is, right? It's like, which person are we gonna focus on? Um, and it adds just this layer of challenge that normally in text or voice, interactions is just, you know, not as common, in the environment to have 100 people talking at the same time.
Yeah, I mean, great example, right? Like, although I can say I've been at some gatherings or parties where, I'm talking to someone, obviously, like, in a room with a lot of people, we humans are really good at source signal separation, which is kinda like technical term for that problem, but, like, if someone over there or whatever is saying something I'm interested in, I honestly do have a hard time maintaining my focus. But in
Shout it out.
vision, yeah, but in vision, we call that problem is called context, right? Like, how can you do scene understanding, when the goal is to whatever, navigate an autonomous vehicle down the road or, help a surgeon figure out what's the right tool to pick up now or that they just missed a suture. When the visual field is indeed rather complex and that like attention that you have to play through that messy context is one of the hardest problems in vision, indeed.
Yeah, and there's overlap too, right? Like context is hard with language too, and vision can provide extra context. Like one of the reasons humans, I think, are good at making like figuring out what someone actually means is we can track their body language, we can see what their facial expression is like. So there's opportunity there too.
How far away from, like, lip reading?
Oh yeah,
Uh,
good question.
I actually, when I was, I've been a faculty member, for way too long now, since about 2007, I think. And I was originally thinking about when you're a faculty member, you just get started, right? Like you gotta make an identity for yourself and kind of choose a direction that in which you
Mhm.
believe you can succeed, and there's not too many other people in there. But if you're alone, then no one's going to care about what you do, right? So it's kind of complex. But anyway, lip reading was a problem that I was interested in exploring, and this is like 15 years ago or more, right? So at that time, I already felt like we were mature enough to, as a field, that it would be hard to be seen to make a revolutionary advance. Looking back, maybe that wasn't the best decision because I don't know of a tool that you could use still for lip reading. But anyway, I think I've done it right. But but problem selection even, right, is interesting. Even like I have a slide, Josh, to the like exactly to get at what you were just saying about like the complementarity between vision and language, right? Like, so I've been thinking about language almost since I began. So instead of lip reading, I chose vision and language, right? That was my direction since I've been faculty. Like I won a grant called the National Science Foundation Career Award that was all about image to text, like image captioning, in like something like 2008. But I have a slide in which I show some examples of like challenging visual phenomena that are hard to like that have as complex lingual phenomena. Like in one of them is like a donut hole, right? Like I don't know if you know what like Tim Hortons is or like I
Oh,
guess
yeah,
Dunkin'
Timmy
Donuts you probably
Ho's.
know, right? Like you get like pop-ums or donut holes as they're often called, but like the donut hole is actually not the hole in the donut, right? It's the actual thing that results from the hole you cut out of the donut. And like, I mean, unless you've seen that, no one's gonna. I mean, it's hard to describe. It's messy to describe, right? So,
Right. Yeah, if you wanna
but
buy a donut hole and you've never seen one, you think you're just buying air, like someone's
exactly,
Yeah, it's
right?
a
Like,
concept, a delicious concept.
yeah. Uh, Finbit, right? I'm thinking of the name of Tim Hortons, right? Yeah. So, but even like in other things, right? Like, we've done a lot of work in like instructional video understanding, right? That's a common problem in the field right now that I've played a role in kind of emphasizing or creating. Right there are some things that require clearly require multiple modalities, right? Like a typical step of a recipe might be something like add oil to coat the bottom of a pan. Right, but, like, unless you actually like, you read the text or you listen to the text, and then you see the action of the pouring, like, coating the bottom of the pan can mean a lot of different things, right? If I have a big hole in the oil bottle, I might fill it with an inch, deep, but where like, that's not what that means, but I only know that because I've cooked things in way too much oil sometimes, and I've seen the example of it, right? Like, that multiple modality is really key, and I think that's really where, like, vision is, like, coming out is like increasingly in the main stage because like, it's back to the language bits, right? Like you could only do so much by reading textbooks, right? Like as a kid, I was often I don't know, politely ridiculed by my family as being like book smart. But like, the common sense part of it that you get from experiencing things in the physical world or looking at them or doing them and so on. I think LMs are great, but without like looking at things, without touching things, like the actual experience of going through the process, that's why I think visual AI, embodied AI, that's where the field is going, right? Obviously powered and fueled by LLMs, but I think that's the clear next horizon.
Yeah, it's almost like watching a kid learn to ride a bike while holding a book and trying to read how to ride a bike.
Yeah.
You're
Yeah.
like, someone needs to show them. Yeah.
Yeah. Yeah. And even in that example, I mean, I've been riding a bike forever now, but like if you overthink as a kid when you're riding that bike, what you're supposed to be doing, you'll generally fail, right? Or I think the grown-up analogy to that is like your golf swing, right? Like, I mean, I've been playing golf for like 30 years. I'm not very good, but I hit like bogey golf, but like if I overthink my shots, I mean, generally the ball is going to go in the wrong direction because I just wasn't like working through the trust, if you will, in the motor experience.
Well, I feel like singularity and AGI come up a lot, like just when people are interacting with large language models because they can speak so convincingly and they seem to know so much. But when you fold in like the ability to see things and contextualize that way, that
Yeah.
seems like that will be a huge leap forward for
Yeah.
systems and models when those things
Yeah,
are
I
connected.
I mean, I totally agree, right? And I think the connection of these capabilities to actual tasks or actual goals, I think is critical to drive, maybe not even like the next generation of systems, but like foundationally, right? Like I mean, humans, I mean, I'm not an expert in human learning. But I have 3 kids and I've watched them learn, right? Like, I mean, my 7-year-old, I mean, she reads, but she certainly hasn't read all the world's knowledge yet. She's very smart, very capable, right? Can make
Exactly.
herself food, like can interact with people she's never met before. She knows like the social norms of that interaction. Like all of those all of those things are like core to like a sentient being, right? And like I don't even think we're looking at those problems in AGI or AI or like in contemporary AI. I think we realize those rationals among us realize that there's a huge horizon of growth we have to do as a discipline to understand like right like it. I mean, just very concretely, right? The human brain runs on something like 20 watts of power. I just about a year ago or 10 months ago, I bought an 8 GPU box for my lab, 8 H100 box for my lab that I believe needs something like 8 kilowatts of power to run. And like the number of nodes or the amount of data that can process through that is still a tiny fraction of like the actual neurons we have in the human brain. Right? Like, do we need such big models? Like, I think these are like the questions that are being asked are or will be being asked increasingly are a lot. I think it's partially along these lines, right? Like, how do we think more with more principles in mind, with more goals in mind, like in terms of like grounding the exciting work that everyone's doing into a little bit more goal oriented aspects so that we might drive more energy efficient, more representation efficient, more compute efficient type models. And I think vision's a good driver of that, right? Like, I don't know if you've ever seen the experiment, but if you take any image that you can snap, like even the image of this screen right now, or like this foliage outside my window here, like, and you look at neighboring pixels and just take the difference of their intensity value, like vertically or horizontally or so on. It follows an inverse exponential distribution, which means like it goes like this, right? Like, and like the peak is basically when there's no difference between neighboring pixels or like one intensity value difference. Whereas like the tail of that distribution is when there's any big difference, which signifies like an edge or some other content change, which is just to say like in the visual world, there's a huge amount of redundancy, both in like one frame spatially, but also frame to frame in video. And we humans know how to deal with that well. Like that's how as we've grown, we learned about energy efficient processing and so on for what to pull out, what's informative, what's interesting. And there are methods in vision that look at those approaches, but like VLMs or LLMs and so on, right? They don't necessarily they're not sort of looking naturally to exploit those statistics of natural images or like other regularities, because there's no need to be power efficient right now, right? There's like we'll throw as much compute as we need as a discipline. That's like we're in this mindset of like more data, more compute, more power. Let's see what we can do. And then I think when we realize that when that's going to plateau, maybe it has for the LLMs already. I don't know, but then I think we'll begin asking a new set of questions, which are a little bit more like I was just saying, right? Like efficiency in the models, or like in terms of power or representation or goal orientedness. And I think that will drive the next phase of growth. I'm a sort of a card carrying member of computer vision since my doctorate, but like um we often look at problems that we try to be too general in how we solve them, right? Like I want like the most generic image segmentation method possible. Well, I mean, however you segment images depends on the goal that like, what are you using the segmentation for, or like the object detector, like that, right? Like even like to map it a little bit more concretely, right? Like in autonomous vehicles, right? Like one can either like try to detect the road surface, all the facades of all the buildings next to you, all the occluders or like other actors in the scene, like the pedestrian, stoplights. Like you can kind of build that full reconstruction, or you can like shoot radar into the scene, and look for empty space. And
Right.
hopefully the empty space aligns with where you were planning to go on the map, right? Like, right, there are many different ways to solve a problem. And if we don't look at the right goals, I think sometimes we make it harder than it should be.
So when people have said like, oh, once a car can see well enough to drive, like we've taught machines how to see, I think what you're saying is not necessarily because they can see for the purpose of driving, for that specific explicit purpose. But the idea that now we've taught machines to see for any context is not true. It doesn't mean I'm not saying that couldn't be the case, but the sheer fact that it can see well enough to drive does not necessarily mean it can see, well enough to do surgery.
Yeah, 100%, right? I mean, like, how much of the U.S. mail gets sorted by automatic address reading machines now?
Right.
I think the number is like 99%, some ridiculously high number, and it's not a new number. It's not a new system. I'm pretty sure it was deployed. Um, there's a document analysis center at the State University of New York at Buffalo that built the prototype of that system in like 2004 or 2005, I believe, maybe even earlier. Right? Like this has been around for a while, but does that mean computers can read? Right? Like not
Right.
even, right? Like
Yep.
that system was built for a specific task, a specific problem. As far as I understand, like it looks at the zip code part first, and digit recognition's easier than letter recognition. And then it was able to use the digits for the zip code to reduce the search space to understand what street it was.
Mm.
And then when it knew the zip code in the street, it was able to look at what possible house numbers were there, right? Like,
Mm.
or business address numbers, right? Like, that's a great engineering solution to a well-defined problem. General seeing is not well defined.
Right. So
So
we're
That's
gonna
interesting because you think about like Tesla and their approach to self-driving cars is like a car, essentially a car that could drive on any road in the world, just fine. But then, and obviously that's not been easy to achieve. But then you see Waymo making it work because instead of having a car that can drive on any road in the world, they've got cars that can drive on any road in Austin or in San Francisco. And I believe they put some sort of like sensor system in, right, where they're actually providing extra context to make the whole process safer and easier. So that sort of connects with what you're saying, right? Like finding a more like sort of a narrower use case in a way. It doesn't need to be able to drive anywhere, but if it can drive all around San Francisco, that's a really useful thing.
I mean, I agree that we can add value using the advances we have in technology, um, on the trajectory towards sort of like generally useful systems. I'm not too familiar with the Waymo solution. I believe they do actually rely heavily on maps and potentially even like infrastructure modifications, which are fine, right? It's not like either we change the vehicles or we change the environment or we change the drivers, and I don't think the humans are going to change that much, right? So like, or around the vehicles. It is kind of interesting, right? Like, but there's so even in North America, where we're a first world country, pretty affluent generally, like the conditions vary drastically, right? Like, Ann Arbor, where the University of Michigan, where I am right now, right? Like, we actually in the city of Ann Arbor have dirt roads in the city limits. It is not a big city. And I think it's just some like local civil political thing that why there still are some dirt roads, but like, I don't know, they're a challenge to drive on. I have my kids have friends that live on some of these or some of these roads, and like, interesting. Is it, like, would a Waymo or Tesla be able to navigate this road? No lines, a lot of ruts and divots and cracks and so on, right? Like, would I trust that? Or then take another example, like, I was vacationing in Sicily a few summers ago, and right, beautiful place, but we had to drive through a lot of back roads to actually get to the places where we were trying to go to, and like it was hard for me to drive as an experienced driver. So I think you can't boil the ocean, as one of my early PhD students say, right? Like we just have to make progress, and I think we are. And it's just like what frustrates me is just like what you're alluding to, I guess, like the overreach of some of the commentary we
right.
see in the media. We're
Yes.
not solving the vision problem yet. It's a hard problem, but we've made a lot of progress. And let's
Yeah.
give credit where credit's due.
So there's
Even
probably some like scenario here where we have lots of models. So at some point we accumulate enough and some orchestration system that sits in like a meta layer that kind of picks different models for us depending on what we're trying to see and do. And that can give us this illusion that, we've solved it, but it's really just this like cumulative mass of effective models in specific cases. And I imagine that's probably similar to how our brain works. Which is kind of where your tool comes into it. Like it's just lots of people building lots of models.
Yeah, I think that's a fair way to look at it, right? Like, um, there is a well-known theorem in machine learning called the no free lunch theorem, which basically says, there's no one model that will be best in all scenarios. You can
Right.
always construct a scenario in which model one will fail to some other model that we may not know about, but whatever. So, but yet, I mean, given that said, right, there is on any given month, at the end of any given month, right, like there's a battery, like a closet of state of the art model architectures that are generally well used or, appreciated to perform generally pretty well these days. And like for different visual problems like classification or like assigning one label or one or a set of labels to one image or a video, or like detection, like finding an object and its spatial boundaries in a frame and so on, right? There will be different models for those. But like, I mean, totally these days, I mean, even like a high schooler could go and like, be given a problem for, I don't know, botany classification, right? Like go online, find an open source data set for different botany types and classes, pick any model out of a model zoo, like, Torch Vision or our tool at Voxel 51. We have a model zoo with like widely supported models. Put those two things together and get decent performance. And I think that the challenge is when is decent good enough to make, social value or actually bring actual value to the world in a product? I mean, that's right. A high schooler is not going to get there, but like, it's not hard to get 80% performance or 85% performance, on your little open source toy data set that you used. Right. And I think the challenge though, in practice, like the practical work of computer vision and visual AI is what's next, right? Like, if I want to go deploy something that's going to cook it, like, wouldn't it be great? I don't know if you guys have kids or anything like that, but like, wouldn't it be great to have something that cooks your meals and then cleans up after dinner? Like, that would be a godsend to most families. And right, like, but if it breaks a plate every single night, you're not going to want it, right? Or if it like burns your food every other night, you're not going to want it, right? So like, so I think of this as like, how do we get visual AI to like five nines performance? Right? Like five nines comes from the old like network uptime or fault tolerant community, but like basically like how do we get from 80% to 99.999%? Right? That's what's needed to deploy anything. Like a failure once a year. Like if I drop a plate, I think we probably break, I would say 3 to 4 glasses or plates in my house on accident a year. So that's like one failure every 80 days. I'm fine with that, right? So that's something like 99.99% performance for an automated system. However, like if you don't have the right tools to actually do the work, like to actually like figure out how to go from 80% to five nines, what do you do? Like the answer typically though is like just go get more data, right? Like your model, I mean, I shouldn't say that. Like the answer is like, what do I do next? Well, either my model's wrong or I don't have enough data. And clearly, like the easier thing to do is probably just to like go and like look for more open source data or like basically pay someone to get some more data for you, because changing a model is a lot of work, right? Like you have to prove it out and so on, right? So, but I mean, to me, I think that's that's a bad habit, right? Like if all you're doing is looking at the aggregate scores for your model and like the only solution you have or tool you have in your toolbox is to go get more data or go like get more annotations on your data. I think that's a recipe for disaster.
Yeah.
And, it,
We need
and I
that
think,
mixology.
yeah, exactly. Right. Like, I think something like I read an article in, the Wall Street Journal, I think it was, where, somewhere between like 70 and 90% of all generative AI projects are stuck in the okay performance phase. Like they never reach production. Uh, and I think frankly, in my view, that is the reason, right? Like, like there hasn't classically been a good set of solutions or like best practices around going from, okay, this is my performance. What do I do next? And like in our view, in my view, like the real problem is understanding your data, right? Like, that decent performance is about like the mean performance, plus minus a couple sigma, right? Like, so you get like typical performance. and that's the 80%. But like what really matters is in like after that, like the outside of that
Yeah.
space where you have like these corner cases and like the other nuances, and that requires that you really get human with your data, like actually pull it out, visualize it, query your data, and like really understand what the challenges are with the data. So, is it a protocol problem? Is it not enough data for this type of corner case?
Yeah.
Is it like a quality problem, right? Is the lighting wrong in certain cases, or is it like a glare in your view, right? And I think when you have the right tooling to do that, and that's ultimately what we build at Voxel 51 in the software that we call 51 is like exposing basically
Yeah.
like making you be a scientist with your actual data. It's kind of like 51 is like a microscope for ML. And I think
Yeah.
that's
And taking the grind out of it too. Um, you want to show it to us? I'd love to see it. I think
Yeah, let's take a look.
I'm super curious. Like it's almost like a day in the life. I think a lot of people overthink it. I think people would be surprised, like
yeah,
you
sure.
said.
Our software is called 51. And 51 is open source, so you can go and pip install 51. If I wasn't wearing the 51 t-shirt, I'd be wearing the pip install 51 t-shirt, which we give
Yeah.
away at like
I
12
use
hours.
it, so
Right on, yeah. So pip install 51, or actually if you want to just play with it, you can just go to try.51.ai. This is a demo. That's just a similar site, and you'll pull up this shared version of it. This is like the enterprise version of it that we sell as a product, but open source 51 is available. So why don't we do this? So like, let's imagine that you are, let's see, let's imagine you are working like you're an urban planner, right? And you need to get data for your team around like patterns of life for your city to understand like the next phase of road renovations or park renovations, right? Like you need to know where people walk, where people go, maybe even where vehicles walk and go, right? This is like a typical like problem I hear about like for smart cities of the future and so on.
right.
So I have a data
Yeah, it
set in here.
reminds me of like that open source project where they open source satellite images. So now you don't even need to put cameras in
Yeah,
places. You can, yep.
exactly. And in fact, there's a great company called EarthCam, I believe that's their name, that makes like exposes those like publicly available webcams and so on, not satellite cameras, available for general viewing as well. Yeah, totally. Um, so what you're seeing here in Voxel 51's software 51, right? So this is our general browser view. I would think of this kind of like a Google Drive for ML, if you will, right? Like you can share things, you can export things, clone your data sets. You have sort of different views, but let's just focus on the visual data, right? So the main part are all of the images in this one data set. And this is an image data set. And here you can support images, videos, meshes, 3D meshes, and point clouds as well. And you can kind of drill down and like you kind of browse and just get a sense for what's there in the data. But on the left side here are all of the attributes that we have for the data. So, one thing we might do is get a sense for like, imagine like you did this, you trained a model, and for some reason it's not doing as well as you wanted for the like people counting part, right? That ultimately for the urban planning case, you want to do some people counting. So let's see. We should probably try to figure out why we're failing here, right? So let's see. Let's look at the people classes only. So we can kind of drill into that here. All right, it's a pretty big data set, so it has to load the metadata for us. So let's go down and only select people classes. Oh wait, see now I'm already scared as a user of this data set. I'm already alarmed because look, and I didn't realize this. There's people and pedestrian classes. So to me, I don't know. I already don't know what is the difference between those two classes. And from a machine learning perspective, that could be something like class leakage or like confusion in the protocol. So already I'm realizing, wait, I need to go revisit my annotation protocol so I can go and like understand what the difference here is. But what we wanted to do, like say there's a lot of false positives perhaps in this, right? So let's see. Maybe we go down to our model case here and we can look at cases where there are false positives. That's FP. This is available per data set and model run once you've processed the video through our evaluation system, right? So you click on false positives. So now that's changing the view. So it only shows images that the system believes have false positives. So let me see here. Is there one in here that we can go in where we can kind of drill into something that might be interesting? Well, kind of any of these probably are interesting, but let's like drill in. Let's drill into this one here. So, all right, let's turn off the ground truth because that's kind of irrelevant. So this is that cyan was ground truth, and the blue here is like the output of our best model. That would say the current best model. So, I mean, in some sense, look how poorly the system's doing, right? Like they misses all of these pedestrians. It thinks that that is a pedestrian. That is not a pedestrian. That is a garbage pail, I believe, or it looks actually looks like a golf cart, or like a mobile golf thing. But also look at all these things down here, right? So this would be a false positive. These are false negatives that we just didn't realize. But then if we go back, I don't know what we'll find if we turn off the best model and go back to the ground truth. We look at like we missed all of these people back here as part of the annotation, right? So you're already finding problems in the data. There's a missed person down here as well. For example, like this took us 3 minutes to get there, right? Like if you don't really understand, like have the ability to visualize, to kind of query in this way interactively, and then make a plan based on your findings to do something else. Like in this case, I want to go back and rework my protocol. I want to have some notion of crowd of people. And I want to have some notion of the ability, like I can detect my crowd of people and then have a different model that will regress the number of people in that crowd rather than trying to detect every single individual person. I also want to go and change my protocol so that more people that are farther away from the camera for my current problem are actual positive cases and detected. But we can even go a little deeper. And so what I'll do here is change it from whole image view to patches view on the ground truth. So we can get a sense for other potential misses, perhaps that, that we may have missed when actually doing the annotation for the protocol. And, so some of these are definitely people, right? Like clearly person, 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 right? Person. But then I start to get a little bit worried, right? Like I need some more context for this, so I can't really tell. In this image, there really are two people. There are two people, two people, two people. So I'm able to see with just like this one click that if I'm going to be using this data for more than just person detection, my actual goal, like just to map it back to what we were saying like 15 minutes ago, right? Like my actual goal is person counting. I really need to train to set up my protocol and my entire ML lifecycle for this visual AI problem to be really careful about how I annotate, right? This is actually
Right.
a pair of people, not just one. Um,
You have to play capture all day.
you definitely do. Exactly. And the only way to do that is to look at your data. Like, and so there's some other ways of looking at the data as well. So let's look at an autonomous driving case. So this one is an open source data set from UC Berkeley called Berkeley Deep Drive. It has a lot of data around visual scenes that you might imagine are used in an autonomous driving scenario. It has detections. It has classifications about what the scene is. It also has what are called segmentations, right? Semantic segmentation. So we call them polylines in FiftyOne, but basically this blue label means it's a drivable area, right? So that's kind of where the car can go, and so on. So, but look, there's a lot of data. I think there's 100,000 samples in this data set, maybe, sorry, 10,000 or 100,000 in this one that's loaded here, but we can scroll forever, right? This is like an infinite scroll. So what do we do, right? If I don't know where my model's failing, I'm not sure. So what I pulled up here on the right side is what we call an embeddings view. So I can just show you, like, it's generally when you load the app, you just get what we saw with the VizDrone example. But if you want to add other views to the app, like a Plotly representation, some other visual dashboard, we have a model evaluation panel, other histograms over like which different views are there, or embeddings, and all that's extensible, right? So this is an open source toolkit. You can just plug in your own stuff there. And then we select an embeddings key, and then we can split the view just like any IDE for ML or for anything really. And so then we get these clusters, right? So in this view on the right side here, each sample corresponds to one image in the whole data set, right? So let me make this a little bit bigger, right? So you can kind of see each sample is one image. Oh, well, I'll show you how that's true in a case. So let's see, like I can start to look at some of these groups together. I can lasso them and start to play like these clusters, these two clusters that came out of the data, they were just born out of the modeling problem that was given. So this model was designed to classify the content of the scene itself. And we noticed that, look, all of these images here that were in this cluster are night images, right? So like all of a sudden, like in this, it wasn't trained to classify night versus day, but it was a natural separation of the content, which I think is really curious and really interesting. But then you can even get to this and see something like, oh wait, here's an outlier, right? So pretty far from this cluster. So probably a night scene, but what kind of night scene? Well, it looks to me like these are night scenes that might have glare in them. Can I not visualize it? There we go. So like all of those had this really bright headlight, which does kind of change the type of processing that you need to do, right? So if you're in the world of Tesla where you want to use vision only, like cameras only, you're going to need to focus on situations where the visual glare will matter, right? To you importantly. Or you can imagine, let's see, what is over here in this cluster? Oh, look, that's so cool. Like, so look, this is like a rain cluster over here, right? So each of these images seem to have like a lot of wetness on your dashboard, right? You need to know how to do that. So like as an ML engineer in like a day in the life of, when I encounter something like this, I'm like, oh wait, this is an opportunity. These are going to be challenging for me. And it doesn't matter like whether or not, like I can color these based on like the weather label or like the scene label or even the time of day. But if we just use like weather, it'll kind of like show me like, I know it's raining here, right? That's what we're seeing here. I can just turn these off and kind of get that sense that there's rain is scattered about, but this is a specific type of rain. I can kind of validate that. And what am I going to do next, right? Like, what is my action from this as an ML scientist? Um, I would go and basically use these data as query images to my large, like billion large data lake that's living out there in the cloud from all the miles we've ever driven, and pull a huge amount of these samples down and then work with them in a new working set so that I can really see how to attack the problem of rain on the windshield, for example.
And that
And I
kind of
thought
gets
it'd be,
back to what we were saying, that idea that the query isn't language. You're not saying, show me all the images where it's raining. You're showing it examples of images that are raining and then saying, find other images that look like this. And it's
yeah,
the language of querying is the image. And for those who, you know, that wasn't
absolutely.
obvious. Yep.
That's the right angle, right? Like I may not know what or what question I want to ask of my data yet. The only way to get there is to do that type of analysis, to either direct visualization or running like processing through embeddings on it. And then ultimately you get to understand where your corner cases are or other things.
Yeah.
I thought just before, one last thing to show you guys. So 51 supports
Yeah.
images, video as native types. It supported those since it was released in August of
Video is
2020.
super interesting to me, especially as we think about the relationship between objects and different images.
Yeah, yeah, totally. But it also supports 3D meshes and 3D point clouds. So here's a point cloud example that you might also be interested in, like as an autonomous vehicle, like sort of company that
Oh, yeah.
that allows you to have like the ego vehicles in this dead zone in the middle here, but you can have the same type of annotations, and you can navigate around your space and detections and all that stuff for in the point cloud case. And the system supports not only this type of like partial depth point clouds, but also full 3D meshes as well to work with. We try to support all visual data.
It is interesting to think that, like, again, if we find one of the biggest issues when you talked about failures, one of the biggest issues we find in failures is that people try to automate the way they do things, not the way they should do things. And that's just harder because you probably do it in a weird way. And so you're trying to teach a machine to do something in a weird way, in a very specific weird way, instead of just letting it do it the right way. And I think when we think about machines seeing, like you you can't just look at it like having machines see how humans see, because there's LiDAR, there's other infrared, there's things that machines can see that we can't, and utilizing that can make the whole difference, right? It's that
Yeah.
it's that don't anthropomorphize this technology.
Yeah, 100%. I agree that the right engineering solution is to use the simplest problem that most effectively meets your performance goals. If that means radar, that means radar. If that means, visual data, right? Like, I mean, like, for example, in cabin imagery and or for vehicles. I mean, I don't think lidar or radar is that useful in cabin. Fine, put a camera in cabin, right? For drowsiness, for safety for the children, things like that. But for other problems, like why wouldn't we want to use the best solution for the task? But I think what you were saying is true on many different levels, right? Like, indeed, humans, like, I've talked to, I don't know, probably 2,000, maybe more, 5,000 different machine learning engineers or scientists over the last 5 years building this software. Like, as an open source tool, we have a lot of interaction we have a lot of enterprise customers as well. And everyone wants the best out of the system in some sense. But like, one thing we've learned is like each person has their way of working. Sometimes, depending on like the type of problem they're working on, they want to work in a different way. And I think that like natural flexibility is really critical, because like, if I can work the way I want to work, then I will work faster and more effective. I'll do better work. And so we have built 51 to be as flexible and adaptable to different workflows and different work styles as possible.
Yeah.
That's why it's pluggable, extensible on the front end and the back end. It's not a SaaS solution where you go and create a web account, you can't ever see the code. It's open source. You can download it and work with it and things like that. So
It
that
really
was
is like greenfield, at least my perspective, because it's not just the visual components. You've got like a transcription potential aspect to it, which is audio. And then you have um, audio that isn't language based. So detecting, you know, glass breaking and door closing. And there's so much left to do. There's so much left to do. And in that exciting sort of explorative way, to just try to capture um, the information that exists in video, uh, and utilize it to train machines. It's like yeah, it's
Yep.
exciting and complicated.
I totally agree, and I feel like I would be remiss if I didn't show you a video inside of 51. So let me just quickly do that as well, since
Yeah,
it
let's
is
check it
like,
out.
I mean, I've worked with video for a long time, as an academic, and now at Voxel. So let me just bring this back up and just show you a video, just to show you that we do support video. We have our own video player. In the video player, you can even like zoom in while the video is playing to a specific object and everything. Like, pretty powerful analysis capabilities when it comes to the
Hmm.
work that you might do with a video machine learning system. But I won't show too much there. But just to
Yeah,
show we support it.
yeah, and it's like to me it's obvious, but to not everybody, you know, it might to everybody it might not be obvious. But the video is just a bunch of images. It's
Mhm.
it's just a bunch of images, and you analyze each one, and what's happening there is it's just so fast. Each image is being analyzed and classified, and objects are being recognized, and in such a rapid pace that it it looks like a box is moving, but it's really just recognizing it image after image. Um, and it does, yeah. So now we get into like just as there's so much information in a still image. There's like ton more in a video image because you have this temporal aspect to it, um,
Yep.
which is exciting.
So do you want a thought experiment? I don't know how much more
Yeah,
time we have here, but I can give you a quick thought experiment.
we'll wrap it
Uh,
up with that. Yeah.
all right.
Yeah.
So yes, the visual world is complex, and it is significantly more complex than you want to believe it is, right? So imagine you have an image that is just 10 by 10 pixels, right? Like a very tiny image, right? Like a typical image we have, like HD is 1280 by 960, I
Right.
think. something like that, right? Like, so in this 100 pixel image, now even make it even just as simple or more simple, right? Like imagine every pixel can only be black or white, on or off, right? So it's the binary image of 10 by 10. Would you agree with me when I say that image cannot really describe that much? Maybe the digits and the characters of most alphabets, probably not Asian characters or Chinese characters, but it's not going to be able to describe like faces very well or actions or logos, right? Well, in that space of images, there are 2 to the 100 power possible images.
Right. Mathematically, yeah.
Mathematically, like that space. So 2 to the 100 is more than the number of atoms in the known universe.
Whoa.
Right. So it's this weird like setup. And now you're talking about video going like even just take 2 of those, right? 2 of those
Yeah.
layered, 2 to the 200. I mean,
Yes.
that's more, it's crazy. It's 2 frames of 10 by 10 black and white video.
What's
Right.
crazy too, when you think about like all the different spectrums of vision that you can add, and then we're talking about adding like layers of language into this. We had a conversation with Dr. Michael Greaves, who kind of came up with the digital twin concept, and we were talking a lot about like how sometimes people focus too much on fidelity, right? Like they want the highest fidelity digital twin, and we're talking about a realm where the fidelity could just be astronomical in terms of the layers of information that could be represented. So like a lot of the real work too is finding like the lower resolution slice that you can feed to the system so that it can do what you want it to do. And it seems like through this conversation, like the way to do that is to find a good use case to build around so that you can
Totally
find
agree.
the relevant information.
Well,
Yep.
this was awesome. This was, yeah, I love vision. So and
Mhm.
I agree with you. This is the year, and we'll see more.
Absolutely. You know,
So much more to come.
when I was a grad student, there was a slogan in my lab, too many pixels, so little time. And I think that's a good way to
2 to the
wrap up the
100th or whatever
conversation.
that was. Yeah.
That's good. Well, guys, this was great.
Yeah.
Really,
Thanks, Jason.
really
enjoyed
enjoy
it.
having
Fantastic.
you on.
Yep. Great.
All right. Well, thanks for hanging out with us again here on Invisible Machines. Don't forget to like and subscribe wherever you get your podcasts. Always remember that you can watch this podcast too on our Invisible Machines YouTube channel. Head over to uxmag.com. We have a podcast page there where you can explore our back catalog and you can look at episodes centered around popular topics. Many, many thanks to our incredible production team here in the US and in Ukraine. Elias Parker, Michael Litvinov, Allison Harshberger, Alla Slesarenko, Vera Pokodkov, and Darina Moskovchuk. Till next week, Owagi.